This is the second of 4 video groups devoted to the structuring numbers instructional sequence. There are 3 video segments within this group. In this video group, we discuss part 2 of the sequence, becoming efficient with adding and subtracting using grouping strategies prompted by the RAG. In many ways, this is the heart of the sequence. More instructional time will be devoted to this part than to parts 1 and 3. In this part of the sequence, children advance from first using their arithmetic racks as they solve addition and subtraction problems posed within the double-decker bus scenario, to using a visual image of the rack as a means for reasoning mentally. By the end of part 2, many students are able to reason using only mental imagery. The ultimate purpose of this part of the sequence is that students develop the conceptual basis for solving addition and subtraction tasks, including missing addend and missing subtrahend tasks that involve numbers to 20 by using grouping rather than counting strategies. By grouping strategies, we mean ways of reasoning based on partitioning the numbers involved in the task into groups that can be easily combined in efficient ways based on doubles, fives, and tens. As in part 1 of this sequence, part 2 begins with an introductory activity that ensures that children understand how to use the rack to show what happens in the scenario, how to show that more people get on the bus, or how to show that people get off the bus. After that initial activity, there are 2 major segments to this part of the sequence. In the first of these segments, reasoning by moving the beads, children use their racks to complete the tasks. In the second major segment of part 2, reasoning without moving the beads, children shift from using their racks to complete the tasks to reasoning with the support of a visual image of the rack. The anticipation activity is a transition activity that supports making this shift. And imagination bingo is an activity involving little discussion that is appropriate after most children can reason easily without moving the beads. The goal is that by the end of this part of the sequence, many children will have developed rack-related number relationships that they can use to solve additive tasks for numbers to 20. These rack-related number relationships form the basis for grouping strategies. After discussing each of these activities, we will turn to a number of pragmatic issues, including productive number choices, recommendations for how to show the initial configurations, and a detailed discussion of pedagogical notation that supports reasoning numerically, and a suggested timeline. The tasks posed in this part of the sequence involve reasoning about how many people are on the bus after more have gotten on or some have gotten off. Initially, children enact the change on their racks. Therefore, it is important that they understand how to use the rack to do so. To show that more people get on, move that many more beads to the left. In this example, the motion shows that 6 more people got on the bus, all of them on the lower deck. To show that some people get off the bus, move that many beads from left over to the right. In this example, the motion shows that 8 people got off the bus, 6 off the lower deck, and 2 off the upper deck. Our experience is that these ways of showing the change in the number of people on the bus are not automatic for all children. Therefore, it is useful to take the time to clearly establish these conventions at the outset. A brief conversation with the class typically suffices. The sole purpose of this introductory activity is to establish these conventions. Activity 2, reasoning by moving the beads, is one of the main activities in part 2 of the structuring numbers sequence. This activity will be used over and over many times. Each task is posed in 2 parts. First, the teacher shows, not flashes, a configuration on her rack to represent the number of people on the bus. The children show the same configuration on their racks, and the class agrees on how many people are on the bus. Second, The teacher states how many more people get on the bus or how many get off. Children indicate the change on their racks in any way they choose. That is, they decide for themselves which beads to move. Then they use what they have on their racks to figure out how many people are on the bus. And there is a subsequent class discussion. Let's look at an example. The problem the teacher has in mind is 8 plus 6. The teacher shows the initial configuration on her rack. Here we show the configuration we have chosen for this example. Children show the same on their racks. There's a brief discussion about how many people are on the bus. By this time in the sequence, this discussion will be very brief. The sole purpose of the discussion is to ensure that everyone in the class agrees that there are 8 people on the bus. Now the teacher poses the rest of the task. 6 more people get on the bus. The children show that by moving 6 more beads from the right to left, doing so in any way they choose. Then the children's task is to use the resulting configuration on their racks to figure out how many people are on the bus now. The subsequent class discussion focuses both on the final result and how the child figured it out, and on which beads the child moved to get that result. Notice that once the child has moved the beads on his rack to show the change, the task he has now is to read his rack, and ideally to do so efficiently. Well, that's exactly what part 1 of this sequence was about, learning to read the rack efficiently. So by now, many students will be able to do so. However, it is important that the discussion also includes talking about which beads the child moved and why, since it is that aspect of the discussion that has the potential to relate to grouping strategies. Before we discuss what children do, I want to remark that it is important for the teacher to allow sufficient time for students to figure out the task before beginning the discussion. In our experience, teachers new to this instructional sequence frequently begin the discussion before children have had sufficient time to do so. When the discussion begins too quickly, only the most sophisticated children will have actually completed the task. The result is that the other children then might not finish thinking through the task. And of course, that means that the activity is less productive for their learning. How do you ensure that children have had enough time? One way is to ask them. Raise your hand if you want a little more time to figure this out. Or to privately say to individual children, "Have you figured it out yet? Would you like more time?" Just to emphasize this point a little more, research shows that teachers often call for a response within 5 to 10 seconds after posing a question. But if we pose a task that requires some figuring out, then surely we need to give children time to do so. What do children do? Returning to our example, everyone starts with 8 beads moved to the left on the top rod. To show that 6 more people get on the bus, children have to move 6 more beads to the left. There's no restriction about how they do so. They can move the beads on the top rod, on the bottom rod, or some on each. For example, here they could move 2 beads on the top and 4 on the bottom, as Andi did. 1 on the top and 5 on the bottom, as Brian did, or all 6 on the bottom, as Carlos did. Once children have moved the beads on their racks and have been given sufficient time to figure out what they have now, the teacher engages the class in a discussion. Before we talk about how the discussion might proceed, let's remind ourselves of the instructional intent of this part 2 of the structuring numbers sequence. It is this: to foster students' use of grouping strategies for additive tasks as an outgrowth of the way they move the beads to show the change in quantity. Or to say it another way, the goal is that children develop ways to solve additive tasks involving numbers to 20 using grouping strategies that have been prompted by the color configurations of the beads. With this in mind, the teacher's agenda is to foster children's conceptual development to that end. Let's look at the way Andi moved the beads and consider how that might contribute to developing grouping strategies. After moving beads to show that 6 more people got on the bus, Andi's rack looks like this. Because of the emphasis in part 1 of this sequence on reading the rack efficiently, Andi might easily figure out that the total is 14 because she sees 10 beads on the top, 5 red and 5 white, and 4 red on the bottom. 10 and 4 make 14. The crux of the discussion comes in as Andi explains which beads she moved and why. For example, why did she move the 2 beads on the top? She might say that she did so to fill up the top. Then the question is, why did she want to fill up the top? Well, if you fill up the top, you have a 10. Having a 10 is advantageous if you just know that 10 and 4 make 14. And this relationship between 10 and the related teen numbers is something that many children will have developed in part 1 of this sequence. As Andi elaborates why she moved 2 beads to fill up the top, either she or some other student in the class will call attention to the usefulness of 10. In this way, Andi's way of moving the beads becomes the basis for beginning to reason by grouping to fill up the 10s. Some children that move the beads in the same way but did not think in advance of doing so to create a 10 might now become explicitly aware of how doing so made it easy to read the result. Of course, for the discussion to be comprehensible, it is important that the teacher shows the solution on her own rack so children can see it as the discussion takes place. The discussion needs to include talking about all of the things we have mentioned here. How Andi added the 6 as 2 and 4. Where on the final configuration we can see the 2 and the 4. How the 10, the beads on the top, are made up of the original 8 and 2 of the 6 added. How moving the beads in that way made it easy to figure out 14. How just knowing that 10 and 4 more make 14 makes this way efficient. Discussions of this type take time. The class might spend 5 to 10 minutes discussing Andi's solution. The time is well spent. Over the course of this part of the instructional sequence, the teacher will pose many tasks of this type and have many discussions that link moving the beads, the way Andi did, to filling up the 10s. Over time, more and more students will move the beads purposely to that end. Brian showed 6 more getting on the bus by moving 1 bead on the top rod and 5 beads on the bottom rod to the left. Here we see the final configuration on Brian's rack. His rack is also easy to read because, like Andi, the way he moved the beads resulted in a 10. He might just know that 10 and 4 are 14, or he might count on by ones from 10 to get to 14. However, there is much more to say about how he moved the beads to get 10. Where does the 10 come from? It comes from the 2 sets of red beads. The discussion will include talking about how one of the 5s comes from the 8 and the other 5 comes from the 6. Where does the 4 come from? The 4 is from the white beads. 3 of those are from the 8, and the other white bead is from the 6 that was added. Notice how this part of the discussion includes talking about beads some of the time and about quantity at other times. This subtle aspect of the discussion is precisely how it functions to facilitate children's linking the way the beads are moved to grouping strategies. The 10 came from combining 5 from the 8 with 5 from the 6. This way of talking about Brian's solution will eventually result in children being able to solve the task 6 plus 8, presented purely numerically. That way of reasoning is the goal of part 1 of the structuring numbers sequence. It is the end point. Here we see the genesis of that way of reasoning. It is based on moving the beads, and it is the way the beads are structured on the rack that makes that possible. We remind teachers that developing these ways of reasoning requires conceptual development. We are not teaching certain ways of reasoning. We are creating the possibility for children to develop ways of reasoning that grow out of their actions and attempts to make sense of those actions. Not all children develop the same ways of reasoning. And since conceptual development is based on what the child already knows and understands, children differ substantially in the amount of time required. There's yet one more way children could have moved the beads to solve the task posed. Carlos moved 6 beads to the left on the bottom rod to show 6 people getting on the bus. And once again, we have a rack that can be read efficiently as 10 and 4 for a total of 14. The difference between Carlos's solution and Brian's solution is in the 4 white beads. Brian had 4 white beads all on the top rod. Carlos had 3 on top and 1 on the bottom. In a sense, Carlos's solution will be easier to talk about in the class discussion because the 6 beads that he added are shown all on the bottom rod. For this reason, it will most likely be easier for children to see how the 6 that were added can be thought of as 5 and 1, and the original 8 as 5 and 3. Otherwise, the discussion will be similar to that for Brian's solution. The 10 came from combining the 5 red beads on the top, the 5 from the 8, with the 5 red beads on the bottom rod, the 5 from the 6. The 4 came from the 3 white beads on the top, from the 8, and the white bead on the bottom, from the 6. It is the color configuration of the beads that contributes to thinking of 8 as 5 and 3, and 6 as 5 and 1. And it is precisely because Carlos added all 6 beads on the bottom rod that this way of seeing the 8 and the 6 is possible. Carlos's solution contributes to developing the basis for reasoning about adding 8 and 6 by partitioning each number into 5 and what remains, adding the 2 5s, and then adding on the rest. Tasks like this, where children use their racks and actually move the beads, are critical to forming the conceptual basis necessary for later reasoning purely numerically by decomposing and recomposing quantities using grouping strategies. In the example we've presented, each possible way of moving the beads led to creating a 10 that could then be linked to an efficient grouping strategy. There are examples where some ways of moving the beads do not lead to results that can be linked to efficient grouping strategies. We will come back to this point later and give an example. Now let's consider a subtraction example. The task the teacher has in mind is 13 minus 6, but she does not pose it that way. She shows 13 on her rack as seen here. Children show the same on their racks. There is a brief discussion to ensure that everyone agrees that the rack shows 13 people on the bus. Next, the teacher poses the rest of the task. 6 people get off the bus. The children show that by moving 6 beads from left to right, doing so in any way they choose. Then the children's task is to use the resulting configuration on their racks to figure out how many people are on the bus now. The subsequent class discussion focuses on which beads the children moved to show that 6 people got off the bus and how they figured out how many people are on the bus now. Let's take a look at the possible ways for this task. What do children do? They move 6 beads from left to right in any way they choose. In this example, there are 4 possibilities. They are: move the 3 beads on the bottom to the right, that is, empty the bottom, and move 3 beads on the top to the right, as Darius did. Move 2 beads on the bottom to the right, and move 4 on the top to the right, as Xavier did. Move 1 bead on the bottom to the right, and move 5 beads on the top to the right, as Anna did. Move 6 beads on the bottom to the right, as Gabriella did. The resulting configuration in each case is shown here. We will discuss each of these ways in turn and consider the potential of each solution to promote children's development of grouping strategies for subtraction. Let's look at the way Darius moved the beads and consider if that might contribute to developing grouping strategies for subtraction, and if so, how. Darius moved the beads on the bottom to the right. That is, he emptied the bottom and he moved 3 beads on the top from the left to the right. Darius's rack looks like this. When called on to explain how he moved the beads, how many people are on the bus now, and how he figured it out, what might Darius say? The resulting configuration of 5 red beads and 2 white beads on the top will be relatively easy by now for everyone in the class to figure out as 7. Darius might say there are 7 because 5 and 2 more make 7. To describe how he moved the beads, he might say that he moved all of the beads that were on the bottom to the right. He emptied the bottom, and also move 3 beads on the top to the right. Notice that there is nothing explicit in what he has said so far that points to a grouping strategy. That is why it is important that the discussion continue to include Darius's reasons for moving the beads as he did. Why did he empty the bottom? As Darius elaborates why he emptied the bottom, he or others might remark that in doing so, he got down to 10. Then he took the rest of the beads away from the 10 on the top. Why did he want to get down to 10? Maybe he just wanted to empty one of the rods. However, it is also the case that by now 10 is a very friendly number for most students, so he might have wanted to get down to 10. From a mathematical point of view, Darius's solution can be thought of as revolving around the relationship between a team number and 10. In this case, that 13 is 10 and 3, and also on children's familiarity with the combinations that make 10. As an aside, those children that do not yet know the combinations that make 10 have further opportunities to develop those understandings through discussions of tasks like this one. In other words, Darius's way of moving the beads can be the basis for an efficient grouping strategy, first grouping down to 10. Notice how this grouping strategy is essentially the reverse of the filling up the 10 strategy that is implicit in the solution Andi used on the additive example we discussed earlier. One function the teacher serves is to ensure that the discussion includes talking about these number relationships and how they relate to the way Darius moved the beads. That is an essential part of the discussion. As children talk about both beads and quantity represented by the beads, they begin to develop the basis for eventually being able to reason by using strategies based on number relationships involving 10. Let's consider another solution. Gabriella's solution was to move all 6 beads from left to right on the top. Her rack looks like the one shown here. When asked how she moved the beads, how many are on the bus now, and how she figured it out, Gabriella might say, I took all 6 away from the top. Now there are 4 on top and 3 on the bottom. That makes 7. As with Darius's solution, there's nothing explicit in Gabriella's remarks so far that point to a grouping strategy. But her remarks suggest how the discussion might proceed to bring a grouping strategy to the forefront. We know that one of the typical ways sophisticated students reason to solve a task such as 13 minus 6 is to think of the 13 as 10 and 3. Take all 6 away from the 10, add the 4 that remains to the 3 from the 13 to get 7. That is an efficient grouping strategy that is based on a comprehensive understanding of 10, the way 10 relates to the team numbers and the combinations that make 10. Gabriella's way of moving the beads directly mimics that grouping strategy, though at this point in time, Gabriella's reasoning is almost surely driven by how she moved the beads. It becomes the teacher's responsibility to ensure that the discussion includes talking not only about the beads, but about the quantities they represent and the number relationships involved. For example, here's a legitimate question. Where are the 6 that Gabriella took away? Gabriella or others will say that she took 6 away from the top. Others will say that she took 6 away from the 10. She didn't take any away from the 3. Notice this shift from talking about beads to talking about quantity. Someone will likely say that Gabriella put the 4 beads on the top with the 3 beads on the bottom to get 7. Someone else might say Gabriella took 6 away from the 10, and that left her with 4, and she put the 4 together with the 3 on the bottom to get 7. These seemingly slight variations in what children say are important because they indicate how children shift between talking about beads, how the beads were moved and what they see on the rack, and talking about relationships between quantities. And this dual way of talking is precisely how moving the beads on the rack to solve tasks gradually over time evolves into reasoning by using grouping strategies. Over the course of this part of the sequence, using this activity and those that we will describe next, the majority of the students will develop 5, 10, and doubles reference number relationships for numbers to 20. These relationships will result in their being able to reason flexibly using grouping strategies. This development takes time, It represents an evolution in the children's thinking and reasoning. Xavier's solution was to move 2 beads on the bottom and 4 beads on the top from the left to the right. His rack is shown here. As Xavier explains how he solved the task, he will talk about how he took 2 beads off the bottom and 4 beads off the top. Now he can see 6 on the top and 1 more on the bottom. That makes 7. As with the 2 previous solutions, it's relatively easy to figure out the 7. As the discussion continues, children will talk about where the 6 are that Xavier took away. He took 2 of the 6 away from the 3, and he took the other 4 of the 6 away from the 10. These remarks link Xavier's movement of the beads with quantity. So here again, the discussion involves shifts from talking about beads to talking about quantity. However, there is a big difference between Xavier's solution and the 2 that we have discussed so far. From a mathematical perspective, Xavier's solution involved thinking of 13 as 10 and 3, taking 2 from the 3 and taking the remaining 4 from the 10. He then combined the 1 and the 6 that remained to get 7. Well, this is also a grouping strategy in the sense that Xavier partitioned the numbers involved, subtracted the amounts needed, and then recombined the quantities that were left. However, it is not an efficient grouping strategy. Likewise, Anna's solution method, which was to take 1 bead off the bottom and 5 beads off the top, seen from a mathematical perspective, is not efficient. Described mathematically, Anna thought of 13 as 10 and 3, took 1 away from the 3, and took the remaining 5 that needed to be taken away from the 10. She then combined the 2 and the 5 that were left to make 7. The discussion of Anna's solution will no doubt also include talking about beads and about the quantities they represent. But the grouping she used is not efficient. We will come back to these 2 solution methods later to explain further why we say they are inefficient. While in both cases the discussion will include talking both about beads and about quantity, these ways of moving the beads will eventually drop out because they are not efficient. Here's what I mean by saying they will eventually drop out. As tasks of this type are used over and over in many lessons, children begin to anticipate what the final configuration of the rack will be, even before they move the beads. And as they do so, children increasingly begin to use the most efficient ways. And that leads us to the next instructional activity, one we call the anticipation activity. That activity and the subsequent activities are described in the next video segment, 2B.